So briefly, what that is with current development, like urbanization, agricultural work, we are altering the flow, the natural flow of the streams. And sometimes that can be detrimental, leading to things such as erosion. Erosion can be bad for numerous factors, loss of like land and property, but also for aquatic systems. It can be bad by transporting sediments farther downstream. So that's why we're working on this. And so we have two sites that we're taking a look at. Both of them near Duncansville. So our two sites are probably about 20 minutes away from here, about 4 miles apart. If you follow Old 22 down the hill towards like Hollinsburg area, that's where we're looking at. So taking a look at each of these two sites here. One is Poplar Run. So this is the one that's located in Newry, if you're familiar with the area. At this site, if you take a look at the banks here, you can see that there is a good bit of erosion that is occurring here. The erosion with the addition of this site is located adjacent to, or in between actually, two private properties. What you're looking at, this private property here, is actually they're losing their land. So it's important for the landowner, it's also important for the aquatic life. This stream also is a high quality fishery. So when we're looking at this, one of the things that we want to try to look at and preserve is the natural habitat of, or not only preserve it, but improve the natural habitat of the ecosystem here. So we want to make sure that this habitat is good for aquatic species of fish, and we want to continue to preserve that. So in addition to that, we have a large degree of sediment deposition, and that's what we're looking at here, that's what we're trying to preserve. So the other one is Spencer Run. So this is a pretty severe site. It's located on a cemetery and adjacent to another road as well. So this one is if you can tell from this picture, it's a steep bank, probably about 10 feet up. And during storm events, we have like a large degree of sediment, transportation, and erosion. And so we're taking a look at these streams here and trying to find out what can be done to fix this, what can stop the erosion. This one is not a high-quality fishery, it is a warm water fishery, so habitat preservation is not as essential as it is in the other site. Still important, but it's not, we're not focusing on that as much. So for Poplar Run, we're looking at a way to preserve that site by increasing the habitat. This one is literally trying to preserve the stream bank where it's at and stop that erosion.
Some of the constraints for each of these two sites, for Poplar Run, which is the one that Stephen mentioned earlier, we need to look at ecological benefit. For one, it can't interfere with the opposing side. So when you're working with a stream, you have you're able to work with one property owner who owns from the stream bank that they own to the very center of the stream. So the other side, that property owner, we don't have the consent from to work on that side. So we can only work on things that deal with one side of the bank. And then on the other hand, we also need to just look at things that are really going to start making fish hatcheries and the environment for the fish more prominent there. And then in Spencer Run, one of the main things we're looking at is that the gradient of the stream bank is over 10 feet high when you're standing right next to it. So we're looking at only solutions that you can't just throw a log in and it'll divert the stream and it's fine. Because we're looking at something that's over our heads, and so you'll see in the next couple slides that that there's only a few solutions that actually work with this kind of stream bank, and the vegetation there is very thick, especially in the spring and summer months. So that could be an issue when we're looking at what kind of equipment are we going to have to get in here. And the structure of property is located right next to a cemetery, which we'll show you. This is actually Bob. You want to click? Sure. Yeah. So this is Spencer up here. You can actually see the grave sites right next to it. This stream comes along here, and it's eroding this side of the bank, as you can see, because it's coming in at this angle, and just tearing away the bank there. So first we lose the road that the cemetery owns, and then eventually grave sites, which is obviously a huge issue. And this is the Poplar Run, so you can tell this side, we're working with this property owner, and so we can only work on this side of the bank rather than something like a double wing deflector or something like that. So here's some of the different solutions that we've come up with. We've kind of narrowed it down to just 2 for each one. For Spencer Run, these turf reinforcements mats, like I said, there's only a few different solutions that work with high slopes like this, and this is one of them because you can tell you're basically pinning a mat that's holding the bank together and keeping the water off of it. And the other one, it's sort of the same thing, except for now you're putting, basically you're growing grass right on it, and then you're driving a stake down farther back into the bank that you're connecting this mat to.
So at Poplar Run, where we're trying to preserve the habitat, we're looking at more structures that are, this kind of shows a variety. So deflectors or vanes. So this can show, in this particular example, it has the flow coming down, and they're kind of angled downstream. It can actually work both ways. It could be angled upstream as well. If it's angled upstream, it works in a similar manner, but it adds a little more aeration to it. So basically what's happening, these are going down into the stream at an angle, and it creates a little eddy space around here, which is good for fish habitat. And it also diverts the main flow into like a channel down the center of the flow. So it's going to take the pressure off the side of the bank. So we haven't identified exactly what we're doing yet, but these are examples of, they're pretty good examples of what we're looking at. It puts us in the right direction. So when we're doing this research at the current state, there's lots of examples of this stuff all over the place. We probably have, I don't know, 50 different examples, but by looking at that and thinking about what we want to accomplish and what is feasible to do, we've kind of narrowed it down into these ideas. We're not these are not etched in stone or anything, but it's a good example of what we're looking at. Here actually is an example of one that is faced upstream. That's a log vein. So the veins can come, and they can be rocks, they can be logs. Basically, the idea is that you're going to have a heavy enough structure that's going to be able to maintain to absorb the flow of that water at high and low flows, and be able to divert that water into off the bank.
So this is something we had to do for the actual class, is create a work breakdown structure. And basically, looking from left to right, it's telling us what is our plan. So if you were a potential client and we came to you with this project, we're trying to sell you how we're going to get this done in a certain amount of time and in what order. So first we're going to look at it and say, you know, gathering background, analyzing the stream geometry, stuff like that's very, the first step. You know, you're going out into the stream, you're looking at it, you're seeing, you're surveying, and also you're looking into what kind of solutions, like we've shown you before. What are we going to use for this that you know has to do with this exact site? Like what kind of solution is going to work best? And then next we move on to actually designing and figuring out a budget for the supplies needed and the amount of work that's going to be needed to be done. And then probably most important is the permitting and report writing. We've been told numerous times that this is going to be a huge part of engineering. So at the end, if you don't get the permits, you can't do the project. So this is going to be later on, obviously, because we're still on this step. But the permitting part is going to be huge, and making sure that we are allowed to do what's necessary. So.
Okay, so with that in mind, we kind of broke down our gathering information into like 5 main steps. Getting historical data, physical data, which are kind of one and the same, but it's taking a look at that site. We do aerial photographs. We would go, next week we're actually going to get a survey of this site, which will give us a good cross-section of the river, let us know the exact steepness of the slope. It'll let us know the slope banks and how severe they are. It'll let us know the cross-section of the particular area of the stream that we're looking at. We will gather some soil data that can be found on NRCS, and there's a website which you can go to. You can find online. You can find your exact area. It'll give you information on the soil, which is good because it'll give you like the density, the porosity. That'll let you know for us, how likely is it to erode? When it does erode, how likely is it to go, or how far will it go downstream? And those are all the really important variables. Or if we're using that geotextile stuff, do we need to account for how steep or how deep we need to put that into the bank? How is that going to hold? Do we need to take other variables into account here? So collecting data, now can you go back actually? Real quick. So then from there, what we can do is we're going to do more calculations. So we're going to collect also historical data on rain events. So that should give us also an idea. If we take that with the catchment area, should give us a good idea of the kind of flow that we're going to be looking at. What type of storms, how likely are they to occur? From that, we can use calculations, things such as the Manning's equation, to compile that data and give us a good indication of, what are the regular storm events that we're going to be occurring with here? What type of water flow? At what level is it going to reach in the bank? How high do we need to go? From there, we can create the models, and then moving on to the economic cost here. So this was difficult to do, obviously, because we've never done it before. But the way that we came up with an estimate, and because we don't have anything refined yet, so we don't have the exact idea of what's going to work best, and basically the cost is going to come into account there. We can maybe find something that is going to be ultimate, but what's cost effective as well. So what we did is we looked at two different sites, or like we went about this two different ways. One was we found a website that gave us a cost per linear foot, an estimated cost per linear foot of what it is countrywide to restore a stream bank. So what we did is we kind of extrapolated that. We took a look at, okay, so what type of a section are we looking at? And then basically just did an estimation. We're looking at a cost of about $78,000 there. The other way we did is we took a sample from a similar project here in Pennsylvania on a stream bank that was about the size of ours. On there we found the costs that they included, and we extrapolated that into what we would need for our stream bank restoration. And we actually got very similar numbers here, about $82,000. So we did an estimation, rounding those two, to about $80,000. Now we're going to give you this information, but if you were our client, we would not give you that information. We would tell you it's something more like 100 or over 100 because we want to overestimate. So therefore, when we do reduce costs, we look really good, as opposed to saying this is 80,000. And because there's so many uncertainties at this point, there's a high likelihood that it could be above that. And so, we would want to round up there. So, yeah, that's it. Thank you. Save questions for the end. You can meet us afterwards. Yeah.
All right, Chlorine, you're up.
You got this booted?
Oh, it's by himself.
Oh.
No, I got CJ. You're gonna go for it.
Oh, it's too late, I pressed the button.
I'll push it again.
I did.
You might push it a few times though. Again.
Oh.
Yeah, boy.
Did I get it?
I don't know, one more time. Go one more time. One more time. One more time. Right there, right there.
Sure thing, go. I was trying to get out of it. Which one did you use earlier for time kills?
Use that cord issue.
It's fine.
Not.
It's fine.
Do they have an actual HDMI?
Dr. Bancher's keeping time, not me. I said Dr. Bancher's keeping time, not me. Are you keeping time?
Okay.
Okay, here we go.
Okay, so hello, my name is William.
CJ West.
And Lydia is not here right now, she's absent. But our project is the assessment of the SF3 drinking water treatment plant and modeling and potential improvements. Here's the team members. Lydia is the team captain, she's kind of in charge. I am the team scribe, so I kind of take the notes, keep the files organized. And CJ, he's our water sampling technician. Some other parties involved, Mr. Sean Simmers, he's our technical advisor. Dr. Goodwill, he's our project manager. And I guys know who Mr. Ronald Woodring is, he's the water facility operator. And Miss Kelsey Palmer is our lab access transport advisor. Just some background on the plant. The plant was built in 1998. It started service in 1999 in July. The source of water is groundwater. There are two 90-foot wells that pump the water up from the ground. The chemical addition within the plant, they use aquamag and permanganate, which we will explain a little more further on in the presentation. But essentially, the aquamag is used for pipe corrosion control, and permanganate is used to precipitate out any iron and manganese. There's 4 manganese green sand filters in the plant, 4 carbon filters, and on a daily basis, usually use about 90,000 gallons of water, and that is between Loretto and SFU. Those are the 2 clients that that's close with. There's a reservoir tank that holds 300,000 gallons of water, and then a treated water tank can hold 500,000 gallons of water. For those who don't know what green sand filtration is, it contains glauconite mineral coated with manganese dioxide. What it does is it oxidizes soluble iron, manganese, and hydrogen sulfide gas, and it filters the resulting particles. There's a lot of manganese usually in groundwater. That's one of the reasons they use this type of filtration. The activated carbon filtration in the plant, there's THMs, which are trihalomethanes, and what that is the organic contaminants, naturally or man-made organic matter produced by decaying organic matter in the water. And they can be treated with the activated carbon as prior to any chlorination in the plant. And it also assists with any taste and odor situations in the water. The chemical addition in the plant, like I said, the aquamag, is used to prevent any corrosion in the pipe. The iron galvanized piping and lead copper plumbing, which is usually what's used. It minimizes microbial influence corrosion, and it also controls the iron and manganese. And the permanganate, it is a strong oxidizing agent, and it is used to replenish the manganese coating on the green sand filtration just to the lifespan longer, regenerates the media pretty much. So as of right now for the fall, our goal is to assess the plant in the spring to model any potential improvements. Right now we're kind of in a predicament, we're not too sure what exactly we want to do, but some possibilities we have is to access the carbon filters because they're not really used. Mr. Woodring told us that they're not really that important, but at the same time it's not worth spending money to get rid of them. There's also a problem where it could be, the iron could be precipitating out before the permanganate treatment, and that could just affect the cost. It could make it cheaper if they put too much in. There's an unused storage tank that we're going to possibly try to bring back, and there's a possibility of unaccounted for water. And what that is they're treating more water than what they're actually distributing out. There's a certain percentage that you want to stay in. If it's too high, it's just cost issues. Anything with regulatory. Here's a diagram of the plant. This is a brief description. Here's where the 2 wells are that pump up the groundwater. It comes into the untreated storage tank. And this is where it goes through to the 4 manganese and 4 activated carbon filters. And here it goes through those. The water gets treated, it goes to precipitation. Or it can go back this way for any backwashing. What that is just to backwash the filters, just keep the lifespan going.
Alright, and this is where I come in. Through a work study under Professor Goodwill, I have to go around and take water samples around campus here and test it for manganese, total iron, and total chlorine. And by doing that, get a little sample, put it in a 10 ml cell. You insert a blank cell of what the sample is supposed to look like in this DR900 colorimeter. You take it out, and then there's a set method in which you prepare your sample that you're going to read using colorimeter. You insert your sample and just press read, and it pops up that there is this many milligrams per liter of manganese, iron, and chlorine in the sample. And by doing that and walking around with the GPS, we can get date and timestamps where we will then make a Google Maps of the campus and the ranges of total chlorine, manganese, and iron. So that's my job.
And after the first round of testing, we tested in 8 locations just around campus, whether it was the dorms, it was the buildings here. And so far, everything's good, so there's no need to worry. These lines here are the limits for each concentration for the water. Chlorine, though, it says in the EPA it's 4 milligrams per liter, which is the max, but that's actually not right. You want to have lower because I think it's around like 0.2 milligrams per liter, because anything really higher than that, it can possibly have byproducts in the water, which is what you can't have those. Yeah, like I said, too much chlorine could result in carcinogenic disinfection byproducts. And as of right now, this is our tentative schedule for the fall. We finished a few things so far. Kind of like right now, what we want to do is we want to learn how to use EPA net, which can be used to model the plant, and that can also help us by changing concentration, changing flows and stuff to see if they can make it more efficient. Also, just want to kind of keep testing. We want to go test at the treatment plant. We're kind of waiting for a time that works for us and Dr. Goodwill to go there, because he's really good with grease infiltration. And just to model it, and that's it for kind of the fall, just kind of find out what we want to fix. Also what our focus is going to be on. And that's it. Any questions?
Easy, Jay.
That was me. That was a moment was created from the weight.
There's no force acceleration or backwards. Alright, so our group name is Alright, our group name is Lactose Tolerant. It's funny. I'm not Hannah, my name is Kevin, this is Josh. And we are doing our senior project on building a device to test consistency in dairy farms. And before we progress, I want to ask, does anybody know how much manure is produced by one cow in a day? Somebody that doesn't know. Just guess. Just guess. How many? 30. 30. Okay, go to the next slide. So 158 pounds per cow per day. So some of these dairies that we're working with have over 1,000 cows. So it all starts with the cow, and it is a milking process. So we are working to keep hygiene to the utmost standard. They are milking, and what we're trying to do is to develop the flushing water, develop a simple test that farmers could use to test flushing water in terms of consistency. Now this flushing water, this is the whole process of flushing. So the cows obviously produce manure, and that manure goes into the free stalls of the freestall barn, which is basically where they are for the entire day. And those free stalls are then washed with this flushing water, which is then processed and then recirculated as flushing water. So it is a very in-house process. They don't lose a lot of water, and so they don't have to keep adding water constantly. So this is a video of the flushing process. You can see the solids still there, and they flush. There are 4 main walkways like this, and they have sand beds in the middle, so you can see both. You can see briefly there was one at the top, and it keeps going on for a while. They flush around 2,500 gallons.
No one's ever done anything like this ever before. So right now we're basically in the researching stage, and we're just kind of looking up stuff about just, consistency tests and more about cow dung. And so as of right now, all the money we spent was gas money, just going to sites back and forth and collecting samples. But next semester, whenever we eventually decide on a final product to use, a final device, we'll spend a lot more money on materials and testing to see what the device works the best and to kind of troubleshoot the final device we choose. And in the end, our goal is to make sure that this device is relatively cheap, that farmers can use it and just keep it in the truck, like a little handheld device. And it's not like a big elaborate machine that's going to be very precise. It's just a test to say, yes, the water's good, flush, or no, it's not going to work. So we had a little thing on this page, basically a little schematic of a map, but it wasn't working when we got here, so I had to kind of change it up. So so far we sampled 3 sites. The first site we sampled at was Penny Moon Farm, and they're in Martinsburg, and they don't flush, but they have a pretty elaborate treatment process for their manure water. So we're able to just collect samples and learn more about it. The other 2 sites we sampled from, they both flush, and they were both in Mercersburg, down south near the Maryland border. And Mercer View, they are a family-owned farm, and they have a little bit over 1,000 cows, I think. And they flush their stalls, and we got a lot of samples from them. And then his songs, actually, the 2 farms are both family-owned. They're both the same family. It's kind of cool. His song also flushes their stalls, like I said. But they have less cows to deal with. They have, I think, 700 or so. But yeah, that's the sites we went to so far. So when we're there, we collect samples at different times in the processing of the waters. We collected samples right after the wastewater was anaerobically digested, and that's when it's going to be the worst, because I have the most solid materials in the water. And then we also collected samples in their primary settling pond. They have 2 settling ponds, and we collected samples from both of them. Primary settling ponds have less solid material than after digested effluent, and then the secondary settling ponds have less than primary settling ponds. So the process get better and better, less solids. And then obviously we sampled the flushing water, which is of the best quality with the least amount of total solids in it. So as of right now, we took our samples and we did a couple tests. The first thing we did was a settling test. We kind of just put them in jars and let them sit for a few days, a few hours, and we just periodically checked it out, see what kind of solids settled out in X amount of time. And there's not a huge difference, but there's a difference. There's more solids in the anaerobically digested effluent than there is in the other settling ponds. And then we also just put these samples in little thin bags, and we kind of just felt them and played with them just to see if they felt different from each other and if they had any physical appearances that you could distinguish them from. And the final thing we did was a total solids test, which was the most beneficial. And we just took a couple samples. I think we took 50 milliliters of each sample, and we cooked it in an oven at 106 degrees Celsius for 16.5 hours, I think it was. And we just weighed before and after to see how many solids were left in the water. And it basically worked out where like we thought it would. There's more solids in the anaerobically digested effluent, than there was in the primary settling pond, than there was in the secondary settling pond, than there was in the two flushing ponds, or flushing waters.
Okay, so the test that we're actually trying to develop is a consistency test. And it differs a little bit from viscosity, but not too much, they are related. Some of the consistency tests that are out there that we will probably test in some ability in early next semester. One of them is the Bosphorus consistometer. These are dealt with a lot in the food industry. They have a little more viscous liquid that they're designed for. So that's pretty much the trouble that we're having, is designing a consistency test with accurate testing from data that we can do in a lab to test very low viscous, basically water material. And so that's kind of the problem that we're at right now, and we keep researching about it. Another test is the slump test. You might have heard for concrete. It's where you just like measure the height of the concrete after you pull that up. And another one is the Adams consistometer, where you basically have, it's the one down on the right, you basically have some sort of viscous fluid in that cup, and the cup raises very rapidly, and it displaces the fluid out on this measured ring. So you can tell by how far it goes in a certain time period. The consistency is based on these empirical data measurements. So we're basically trying to develop something similar to these, not exactly, so that farmers can easily test the consistency of their flushing waters.
As Ken said, these tests they test different material, you know, like ketchup or concrete. So the water, if you did it on any of these tests, it would tell you nothing. It's just way too, not vicious, I guess, viscous. But yeah, those are for thicker fluids.
Okay, and so basically our next step is to develop theoretical designs based on the data that we are collecting, develop our preliminary methods and devices. By the end of this semester, we hope to have a few devices in the works, at least a few ideas for them. We're not going to start building until next semester. And we will develop a working on-site device by the end of the next semester, or the end of the year. And then we will hopefully be able to finalize it and develop an operating manual that goes along with it. And hopefully that will allow the farmers to quickly and easily, within a matter of seconds, know the consistency of the flushing water that they're sending down their freestall waters. So
Do you need this?
It's not dirty, don't worry. I got from up there. Wait, like,
Oh, so
time's
you
up.
like blow your nose
No,
in it?
no, next time, not me.
I'll do it.
We good?
Mhm.
All right. Hello, everyone. So our team, we're called Tiny Office Big Hearts, and our purpose is we are designing a tiny office that is entirely energy independent based on the tiny house movement. So the team members we have, I'm Dalton, I am the team leader.
I'm Dave, I'm the team reporter.
And then Caleb is not here, but he is our,
He's our scribe.
there we go, couldn't find the word.
Good job. He's
Good
the
job.
face.
All right, so just some background information for you on our project. So our client is the St. Francis University Energy Institute, and what they want is that they want a tiny office that is both mobile and designed based on the tiny house movement. Now, for those of you who don't know what the tiny house movement is, over the past several decades, American houses have continued to get bigger in space, even though the average American family has stabilized and gradually gone down a little bit. So the tiny house movement is, it's basically designed to kind of bring the size of a house back down, make it more energy efficient, and make it more along the lines of what the average size of an American family is. Now, the Energy Institute
wants one of these tiny houses designed for them as an office, and it also needs to fit into a couple different constraints of they want it to be energy independent, so we don't have to hook up to any external source of energy to charge and power the house, and also it needs to be able to accommodate 2 instructors as well as 10 students, because this thing is going to be used for outreach and be brought around different schools to show off renewable energy, as well as just like a cool, basically like a cool project that's showing off the energy while still being fully functional for the Energy Institute. And our purpose is to design it and make sure it's entirely energy independent. So the functional purpose of the tiny office, as we said, will be to be a display of renewable energy resource systems. So this house will be entirely off the grid, and it's also going to be able to hold meetings and classes. So that way the Energy Institute, any meetings they have can be held in the tiny office. So they're running based entirely on renewable sources. And then also can have for classes. So we can bring students in, students can look around, they can understand that they're like in a place that's entirely running on renewable energy. And also part of the design is it's going to be able to give lectures inside this little office. So the key to success, the first and probably most important thing is that this tiny office needs to be energy independent, and it needs to be run on what we call 2-day autonomy. This means that it must be able to run for 2 full days without having any sort of energy charging. So any solar panels they're not getting enough sun to them to actually charge the batteries at all. Any sort of wind energy is completely useless. So it needs to be able to run for 2 days on its battery power alone. It must comfortably be able to fit the 2 instructors as well as 10 students, which has been a major tipping point for what size we're actually going to make the tiny office. And then it needs to be powered to power everyday office appliances. So the 2 instructors are each going to have a computer they're going to need to have hooked up inside. You're going to need to have a projector that you're using like we are right now to give lectures to the students. You're going to need to have different power outlets for miscellaneous sources such as charging cell phones or charging other things. And then we're also going to have an HVAC system within the tiny office, as well as just the basic lights needed for inside. So some constraints and criteria that we have for the tiny office is that in order to not require any extra permitting, the house needs to be under 10,000 pounds and under 40 feet in length. Other than that, we're going to need like extra permits to get and basically have like a CDL license or whatever. And then it also needs to be towable by our Suburbans. So we need to figure, so our Suburbans, however much they're able to carry, they need to be able to carry it to haul this thing. Otherwise, we're going to have to buy whole another vehicle or rent one to be able to bring the tiny house everywhere, which would be, and it would be far more efficient for us to have and use the own Suburbans. And then budget, we have a $75,000 budget approximately based on grants the Energy Institute has already gathered, as well as grants that they are hoping to have by the end of this month and by next month.
Okay, so we are looking at 2 different sizes for this mobile office. The 2 designs are 8x20 and 8x28, and that's like the walkable space inside. With the 8x20, you have it's smaller, so it's energy efficient and it's easier to pull with your Suburbans or truck or whatever. But it's also smaller to work in, and it's more cramped to store stuff. And with the 8x28, it's large enough to comfortably seat the 2 instructors and 10 guests. And you have more area for solar panels and more room for storage, but it's also more energy demanding with heating and cooling and tiny bit with lights. And then it's harder to pull because it's a little bit bigger. So you need to harness the energy somehow, and to do that you can use solar energy, wind energy, or biomass technology. But we're going to mainly focus on solar energy just because it's easiest for what we have to work with. The solar panels will be housed on the roof of the office, and they'll be constantly charging, and they're open. And then we also have wind technology that we can use, but the problem with wind technology is you need to be like 30 meters up in the air to get like decent wind to produce a lot of power. And to do that, you need like a collapsible, like telescoping pole, and then a large wind turbine with like big blades and stuff. And that's just not feasible to like house in the office, whenever it's already like tiny. So that's just something that we need to work with. We were thinking about constructing a very large tower on campus with a large wind turbine, and then you just plug that in to your office and charge it while you're here on campus, but not whenever you're out and about. And you could also like display like a tiny like little cute wind turbine for like the kids that are like trying to learn about renewable energy, just for like display purposes only, and that would have no functional purpose. And then biomass is just turning thermal energy into electrical current. So to store the energy, we're going to use a battery, and the battery must meet the needs of unstable grid energy, and that is heavy cycling, which is like, some days it's gonna be like a nice week and you're gonna be like charging it, and other days you're gonna be like on the road, like okay, so now we can set up the charge. Okay, now you gotta go. It's not charging. It's charging. It's not charging. And you're using power, and you're not using power, but charging and charging, but like not. Like that kind of stuff. So yeah, you want a battery that can handle that. So one of the best batteries for solar power is lead acid batteries. They're good for off-grid technologies, and they're cost effective. They're about half as expensive as a lithium-ion battery. And the lithium-ion battery is the most common battery, so they're well understood, but they're more expensive. The lithium-ion battery, if you use them and you get a prismatic lithium-ion battery, it's just a type of lithium-ion. It has corrugated sides to it, which has air, just airspace, so it cools down, so the battery doesn't get as warm, which would be, like a nice. You don't want to overheat your battery in an office where people are going to be living. And it's lighter. And the lead acid batteries, they're about 200 pounds. So if you need to move it around, you might want to grab a buddy. So to figure out what kind of battery we needed, we went online and we found a battery sizing calculator. And we just like inputted our voltage and our depth of discharge duty. And that's basically like whenever you use a battery, you're not draining, like whenever you drain a battery and your battery dies, it's not really dead. Like there's still like a little bit of juice in it, but it's just like unusable. And you really don't want to drain your battery down to 0%. So you keep like 30% in there, just so that way it's like not harmful to the battery. And then we're going to use a flooded battery, which is it's a wet type of battery, because you could have like a wet cell, a dry cell. But like the flooded battery, you would need like maintenance to make sure it stays wet and everything's working like this. And then we have our energy load. It's a pretty rough skeleton of what our energy load is going to be. So we have LED light bulbs in the roof for lighting inside the office, a projector, the computers, and the heating and ventilation air conditioning system. And you can see that the main power draw is from the HVAC. So whenever we like focus on storing power, we're going to need to store enough power to keep that running, or else you're going to be cold or hot.
And that's also something that jumps into with the size of a tiny house and how it's a little difficult, because while we want more room to house the people better and make it more comfortable and actually usable, the 8x28 is a full 40% larger than the 8x20, so there's a pretty big increase in demand from the HVAC system, and being the most demanding part of the entire office. That means that we're paying close attention to that and trying to figure out how the size and how much HVAC we're going to need. That's also dependent on how much battery power we're going to need.
Yeah, I basically just said all that. We got the loads and stuff. So here's what the batteries would look like. They're about like, this battery is like 3.5 feet tall. So that's the big boy, and then you got another smaller one that does about the same, but it has they're very similar, but this one the top one would be like, you know, let's say for like if we have the budget and like you're not afraid of like moving around, like that'll be the better battery to pick.
All right, and then for some future plans here, this is just going on based on what we have so far, is we're gonna look more into the batteries, well-sized battery, because the way we have our calculations done right now, and we need to verify, make sure that they actually are correct. The current battery that we want to use is basically overkill compared to the energy that we're going to need. Like, it can store 4 times the energy that the entire office would need running everything 8 hours a day for 4 days straight. So we're going to look into that as a possibility of the battery might be overkill. We might be able to settle for like a lighter load of batteries, which would make things a little bit easier to distribute weight-wise, as well as also easier to maintain, because trying to work with a 200-pound battery is just going to be a pain in the rear. And then we're also looking to explore the incorporation of wind, which, as we said, really the only wind option that would make any sort of sense is to utilize an actual wind tower that's set up over by Stokes that had a windmill running in it for a couple years, but has been shut down the last several years because the company that built it went out of business. So they couldn't actually maintain it, so they had to basically shut it down and take it offline. But if we could get that up and running again, or something similar to it, that would be function as a place to hook up a tiny office, or even just have a small windmill for display. And then energy level with more draw, so we need to refine the energy draw more, like actually take into consideration people charging their cell phones or other miscellaneous power. And then we also need to look into inverters, because whenever you're working with solar energy comes in as DC current, direct current. So you need to actually convert the solar from the DC that you collected as and turn it into AC current in order to actually use it for the appliances. So now that we have ideas of what we have for solar power coming in, the battery power we're going to have, and how we're going to use it, we just need to focus on the inverter, figure out which one's going to be best to convert the energy from solar to battery. And then also the floor plan, so we actually have a design that we're going off of, since our final goal for the project is going to be to actually have like a design to hand to the Energy Institute to say, this is what we think you should build. And that's all we have.